Okay, thank you, everyone. My name is Kapil Katyal. I'm representing Johns Hopkins University Applied Physics Lab, and this work is in collaboration with the Johns Hopkins University Whiting School of Engineering, specifically my colleagues E.J. Wang, Greg Hager, and Chenming Huang. So I'm going to talk a little bit about some of the ideas that we have on pedestrian prediction. We think this is a very important problem for many reasons that was already stated earlier today with respect to autonomous driving, social navigation of robots through crowds. And I personally believe that prediction in general is a very critical component of planning. So I think that as we get more sophisticated in our approaches for control, and we want robots to mimic how humans are able to quickly and seamlessly navigate through environments, I do think that prediction is a very critical component of that. And so this talk will kind of focus on an approach to doing pedestrian prediction, but then also showing how we can use pedestrian prediction to basically modulate the control policy of a robot navigating through crowded environments. So the first thing I want to talk about is the pedestrian prediction approach. So generally with pedestrian prediction, you formulate the problem such that you observe a number of time steps of pedestrian motion, and then you process those observations and you basically generate predictions of some number of time steps in the future. And so what we're doing is we're using a recurrent encoder network. So recurrent encoder networks are very good at processing information that comes in at varying time frequencies. And so we can use the recurrent neural network to basically capture these incoming pedestrian motions at variable times. Then we use a variational autoencoder. So if you remember from Bart's talk, he talked about a bottleneck layer. So a lot of people are using autoencoders to do things like dimensionality reduction. A variational autoencoder is very similar in that instead of just encoding a smaller feature vector, you're actually encoding a Gaussian distribution. And what that allows you to do is you're allowed to basically sample from that distribution and generate multiple samples within your prediction. And then the final piece that I want to really highlight is intent recognition. And I think this is kind of what we thought was a very critical component to predicting pedestrian motion. And really the intuition is that if I want to do long-term prediction of human motion, I want to have some probability distribution about where their goals are in the environment. So there's a door over there, there's a door over there. If we can kind of model those probabilities about where they're going, and then explicitly represent that information and then pass it into the deep network, our objective is to show that does a better job of actually predicting pedestrian motion. And so this figure kind of just describes how we're doing the intent recognition. So we're modeling this based on basically a Bayesian inference formulation. And so effectively what we're doing is we're looking at it as a Gibbs distribution, where initially in the start of the trajectory you have very high uncertainty in terms of where they're going, like what are the possible goals in the environment. But as the pedestrian gets closer and closer towards the target goal, the uncertainty decreases, and you want to basically represent this uncertainty as part of the input to the neural network. And so here, so in this community of pedestrian prediction, there's actually a very common data set or set of data sets that are used to evaluate pedestrian prediction performance. And so all of these are basically, you have a camera on top overlooking some sort of crowded environment, either a university setting or some sort of city environment. What's nice about these data sets is they have the pedestrian positions annotated throughout the whole data set. And so there's 5 different data sets from 4 different environments. And so what we're looking at is the average displacement error, which is like the first set of data. And then that's basically, if I'm predicting 12 time steps in the future, what is the average error across those 12 time steps? And then the final displacement error, which is what is my error at the final, after my 12th prediction, how far did I deviate from what I actually observed? And so we basically have a significant number of baselines because a lot of people are actually working with these data sets, and so we have metrics to compare by. But basically, what we're showing is that on using this approach of kind of probabilistically representing the intent, we're able to improve the state of the art in 7 out of 10 of the experiments that we describe here. And so, I think pedestrian prediction is important, but I think ultimately what we want to do is something useful with this information. And what I think is important for the safety aspect is crowded navigation of a robot. So, obviously we've seen a lot of videos of robots navigating through crowds, but I think a lot of us would hesitate before we'd say that motion is very natural, right? It's very, you constantly freeze when there's really no reason to. I don't think you would ever describe a robot moving through crowd as like a fluid, natural motion as a human would be able to navigate. And so I think one of the things that we inherently do as humans is we have an inherent estimation of our risk, and that's based on our prediction. If we're predicting things that are, if our observations are matching our predictions, then I think that we can be very aggressive in our navigation policy. And then I think as soon as our prediction starts breaking down, our observations don't match our predictions, we adjust our risk, and we become slower, we pay more attention to our environment. And so this is kind of what we're replicating with robot navigation, is can we take the prediction, and in cases when we have low uncertainty, where the errors are fairly low, we can be very aggressive in our control policy. But in situations where my observations don't match, I want to be very risk-averse in my controller. And so we evaluated this in a simulation environment. So these round circles represent pedestrians, the star represents a goal, and the colored dot represents the robot, the yellow being the risk-averse control policy, the green being the aggressive policy. And so if we play this, on the left there, on your left, is the non-adaptive policy, the one that's just going to move as fast as it can, not really paying attention to whether I'm predicting things or not. And on the right is the adaptive policy, where it's able to basically reach the target goal. So here's just another example so you can kind of watch it through again. On the left, it's basically just driving as fast as it can, not really caring about how well my predictions are matching what I'm observing. On the right, it detects that this isn't what I've seen before. I've never trained on this kind of big data before. This is new behavior that I really need to slow down and try to get to the target goal. And this video just kind of shows that this approach scales to up to 20 pedestrians. That's what we evaluated, up from 5, 10 to 15 to 20. And again, same kind of thing. Just the one on the left will try to go as fast as it can, but the one on the right will be judicious about how it interacts with the crowd. And so those are great qualitative examples, but I wanted to kind of highlight in terms of like the quantitative metrics associated with this. And so we looked at a lot of different metrics associated with this. So we basically ran this experiment with 500 test cases, and we looked at various metrics, but the most important one is the number of collisions, right? But there are other factors too, so including the amount of time it took to reach the goal, and then also the discomfort rate, which is, even if you didn't collide with me, did you make me feel uncomfortable because you got too close to me? And so what we did was we looked at how these numbers work. So Cadrel and Sarl are state-of-the-art reinforcement learning-based crowd navigation policies. On the first two lines is basically how well those perform when I didn't change the pedestrian motion. So it knew what the pedestrian motion would be, and it does fairly well. There's only 5 collisions with Sarl. But as soon as you change the pedestrian motion to something that hasn't seen in its training, you basically get 70 collisions using Sarl. And then if I just use one class SVN, just a non-deep learning based approach to detect novelty conditions, I only really improve the number of collisions by 2. And then I'll highlight, on ours, when we adapted the policy based on my prediction error, we were able to bring the number of collisions from 70 down to 40. And the next set of numbers really just show, as we scale that to 10 pedestrians, 15 pedestrians, and 20 pedestrians, we have more collisions, but we still outperform the state-of-the-art navigation policies with respect to that. And then really the last video is just to kind of show that this isn't all just simulation, that this can actually run in real hardware. So we have a mobile robot that can actually, it's the MIT race car, can travel about 20 miles an hour and has onboard LiDAR. And so basically using that LiDAR, we can detect pedestrians using a light detector. And we can basically run this algorithm in real time with a Jetson GPU that's running on the platform itself. So to conclude, really I just wanted to take home message is, I do think prediction of pedestrians is an important area. I think it really can be used to detect things that are outside of the distribution that the policies are trained on. And I think by adjusting the risk of your controller policy, you can still reach target objects and you can minimize the number of collisions while doing that. Any questions?
So, does it scale well, does a policy scale well to crowded environments in real time? Like, there are a lot of pedestrians who will be able to detect all the pedestrian motion in real time and like still do the same thing?
Yeah, so we only tested up to 20 pedestrians and within a 5x5 meter space. So, I mean, I think that that's a fairly crowded environment. That was one of the videos. We didn't really evaluate more than that. I think that it would still scale. I will say that in the simulation, you had ground truth of all the pedestrians in the whole scene, which was not realistic with the, LiDAR is typically 270 degrees field of view. But on the physical demonstration, it was just a proof of concept. But I think what we're going to do next is to really push the crowded environment scene on the physical robot where you don't have full visibility of all the pedestrians. And and I think, to be honest, I think it might actually be an easier problem on the physical hardware because I think having all the data of all the pedestrians in the scene might actually make the problem harder because a lot of those pedestrians may not actually factor into like a local policy. Thanks.
Hey, just wondering if the pedestrian stops, then how is the robot handling this case? Because it's not going to the way that the robot is going to predict.
Yeah, so in our training, we actually basically modeled the pedestrians using this thing called an ORCA simulator. And in the simulator itself, we varied the velocity of the pedestrians anywhere from 0 to 2 meters per second. And so it's seen conditions in the simulator of both pedestrians stopping, starting, and so it's able to handle that because of that. But I think if you took that out of the training set, I think it would probably get confused.
So how will the robot handle that? It will go around the pedestrian, or it will wait until the pedestrian starts to move again?
So basically, it's governed by the reward function of multiple. It's a multiple objective reward function, right? Where time to goal is one criteria,
right,
and then avoiding collisions is the other. And so in this scenario, it's going to select an action that it thinks is going to maximize that reward.
I see.
Yeah.
Okay, thank you very much.